Hopefully hitting the record just happened now, right? Okay, good. Just checking. Silence. All right, let's begin. Dear Heavenly Father, we thank you for this day, Lord. We know that all have sinned and fall short of the glory of God, but we know that we can have salvation through faith in you, Lord, that your righteousness can be our righteousness, Lord. We thank you for that. Just pray to be with us today. Help us to understand this idea about tensors and just continue to encourage the students as they work on this course just this semester, that you'd uphold them for your glory, Lord. In your name I pray. Amen. All right, so tensors. Why tensors? So basically the story is something like this. We've seen how to do calculus on Rn and on normed linear vector spaces, and that was good. But there are certain things that we'd like to understand more deeply, and to do that, we need to study tensors and differential forms. It turns out that the calculus on a curved space, or the calculus of a curved manifold, is most naturally understood in terms of these tensors, and more specifically differential forms and vector fields. So we won't get into full-blown manifold theory or anything like that. But what we do want to do is understand the basic linear algebra, at least, of these things. So what I'm going to try to do today is to explain to you what a tensor is, best as I can. So I think the first thing I have to do actually is to explain to you what the dual space is, though. So we have to start back there. So definition: if V is a vector space, and I'll keep it real here for a while. I may want to do some complex things at some point, but I think I'll just gravitate towards the real case here for a while. So if V is a vector space over R, and I'm thinking a finite dimensional vector space, all right, then V dual is what? Well, V dual is defined to be F such that V goes to the reals, and what? What can we say about F? So by definition, F is linear. So this is a so-called dual space. It's a set of linear functions on V. So another notation for this that you sometimes see is that V is equal to linear transformations from V to R, or probably a better, more modern notation would be Hom VR. So that's the homomorphisms of V to R. Now, so this is the dual space. Now, you can ask, what is that? Well, for one thing, it's isomorphic to the vector space, right? And I'd like to describe how that goes. And I also like to describe how to look at coordinates of a dual vector and coordinates of a vector and study coordinate change here. So let's get to that. So let's let beta, say E1, and here I don't mean to, I do not intend that to be, oh man, I was trying to follow Renteln. I'm not sure I'm not sure I can commit to it. I don't intend these to be the standard basis, and I'm not sure. Well, fine. It's kind of ingrained that these are the standard basis for me, but then in more abstract math, especially the kinds that we're getting into, it's often the case that E1 through En are not used as the standard basis for Rn. So I guess now is as good a time as any to break the chains that bind us to that standard notation. So let's do it. Let this be a abstract basis for this vector space V, all right? What's that mean? means it's linearly independent set, right? And anything in V can be written at it in terms of this basis, right? And so if, and we can also let, let's see here, beta bar equal to E1 bar, E2 bar, En bar, all right, be another basis for V, right? So suppose you have two bases, right? If we look at a vector V, we can either express it in the basis beta or the basis beta bar, right? So we have, so for V in V, we have what? We have V equals to a sum, I equals 1 to n of what? X, well, I guess I could say V. And then here's the thing that we're going to do different starting here, and it'll become clear enough why we're doing this before too long. But so if V is a vector, right, then it has indices which go up. So this would be upper I. Now that doesn't mean the power, it's a notation for the index of a vector. And then the E sub I is down, like that. And let's see here. But on the other hand, we also have what? V bar upper I, E bar lower I. Oh, right. Good. Yes. Thank you. So I guess I'm going back through that then. Let's see here. So if we have a change of basis, right? And let's suppose that, say, E bar I is equal to what? Some. And I should probably just give up on change of basis for this first class. If I was smarter. Let's see here. Yeah, here it is. So a lot of what I'm telling you today is notation, but anyway, it's notation we need to kind of get used to. All right, so curses. So the trouble with Renteln is he starts without the up-down index notation, and then he transitions to up-down index notation eventually. Here it is. Here's what I want. All right, so yeah, E bar I is EI, some j equals 1 to n. And then A is the change of matrix. I think I used a P in the homework, but it's not sacrosanct or anything like that. So we have upper I, lower j, like that. Okay. And so if you follow that, remember that homework, what does that imply about the relation between V bar I and VI? So this is essentially this right here. I'll just put a box around it. This is the definition of A, I, J. What was it, Joe? Oh, no. I mean, oh, that's right. Well, that limit stuff was kind of beside the point. That's. So V bar I is equal to a sum over J. And the way it works is, how's it go? Well, A inverse I, J, V upper J. So what this is a claim at the moment, all right? Claim that if the barred basis is related to the unbarred basis in this way, it must be that the components of the vector are related by the inverse of that matrix in that way. This transformation of the basis vectors implies that transformation of the components. So how would we prove such a thing? Well, lots of different ways. Let me try one. So essentially the point is V is V is V. V is geometric, right? And these two different bases are just two different ways of expanding the same animal. So on the one hand, we have V is equal to sum I equals 1 to n of VIEI, right? And of course, that can be rewritten as what? So what I'm going to do here is I'm going to take this EI, right? Here's my game plan. I'm going to take the EI vector. I'm going to rewrite it in terms of the barred basis vector, right? Once that's done, I can equate what I get to the definition of V bar I, which is right here. I mean, this essentially, guys, defines these guys, all right? So, I mean, these are given, right? So once those are given, you pick a vector, then these are the components with respect to that vector. And this is the typical notation. We use the same letter as the vector, but we add a bar or add an index to denote the component. That's a typical notation in this world. So this EI, right, we can replace with what? Sum j equals 1 to what? N. And EI was what?
E bar I over the summation.
Oh, man. Yeah, I'm sorry. I don't even have it yet, do I?
The EI can come out because it's not part of the index, because it's indexing of j.
Huh. I suppose that is true.
You can divide the summation of A upper I lower j underneath the E bar I.
Something like that. Let me just do it a little bit different. I mean, I'm not entirely disagreeing with you, but if I hit this with the inverse matrix, right? So if I do say sum over A inverse, let's say just a second there. I think IK E bar. Oh, I'm sorry. I'm trying to. It doesn't really matter because we can write the scalar multiplication on either side, but as a point of style, I'm trying to follow what he's written here. So this is E bar I, A inverse IK, and I'm going to sum that I equals 1 to n. So what I've done is this equation holds for I equals 1 to n. All right, I'm taking that, I'm multiplying by A inverse IK for each I, and then I'm just adding those together. The reason I'm doing that is because then over here, I get some j equals 1 to n, some I equals 1 to n of E sub I. Maybe I shouldn't, well, it's too late. A inverse IK A, goodness gracious. What have I done? Oh. Yeah, I think you're right. Stink. Scratch this. Ah! Good grief. Just a second here. Where'd that stupid formula go? I'm sorry, guys. So you think what, Daniel? I mean, I know that. Yeah, I mean, I know that. I mean, this much I know. At the end of the day, we'll get this: e sub I is equal to a sum j equals 1 to n. I probably should use a different index or something to see better what's going on here. E bar. Let me use k here for a second. K. And let me call this, well, I'll call it I, fine. E bar k, A inverse, ki. Because I mean, essentially it's, the roles are reversed, right? So it has to be the inverse transformation. But you can derive that if you just solve one for the other carefully, and I can't see it at the moment, and it's taking too much of our time. Let me go on. So this you can get from here to here. Now, so the point then is that this is what? This is e bar k, A inverse k what? I, right? It's this I. Still there. And then what do you get?
Are we still indexing over J?
Oh, sorry, K. Thank you. So what do we have? We have the sum over I and sum over K of what? Well, let me rewrite that. Sum over I, parentheses, the sum over k equals 1 to n of A inverse k I v upper I. What's that? I mean, don't, never mind. It's. Oh, and right, that's out here. Now the reason I'm writing it like that, okay. What's that? Well, I'm just reorganizing the sum. You know, it's still. Oh. Yeah, you're right. You're right. So, what should I do? Indeed. Thank you, guys. K equals 1, I equals 1, 2. You guys are ahead of me. I'd have seen that in about a minute. That's great. That's a very good comment, Joe. It shows to me you really understand what's going on. That's great. So,
Well, I can see letters.
but that's,
I understand grouping.
no joking though. That is why this notation is amazing. Is the positioning of the letters lets you see whether you're right or wrong. It's a very helpful notation, actually, once you get used to it. Now this, on the other hand, is the sum of what? Well, it's also equal to the sum k equals 1 to n of v bar upper k, e bar lower k. So by linear independence of the beta bar basis, what do we find? So I would draw your attention at this point to the distinction between, let's call this 1, and let's call this 2. Right? So the transformation of the basis is called covariant. All right? That's just a name. So transformation law 1 is a covariant transformation. Transformation law 2 is called contravariant. Contravariant, covariant. Now that's kind of old-fashioned notation, but some of you would like to read old-fashioned things, and so it's useful to use these terms. But you see that the basis and the components, they transform inversely, yeah? Now, that brings us to the back to the dual space, all right? Get back to the dual space. So the dual space has a basis which we denote beta dual. So beta dual is defined to be E upper 1, E upper 2, E upper n. So this is the so-called dual basis to beta, where E upper I acting on E lower j is definition Kronecker delta. And to be consistent with the index, we do this. But it's the same Kronecker delta as before. I mean, it's 1 if I is equal to j. It's 0 if I is not equal to j. And then we extend linearly. So EI is a mapping from V to R. Hence, extend linearly. So EI is a mapping from V to R, hence, EI is an element of the dual space, right? And likewise, you define the dual to the bar basis, right? This is the definition, all right, of the dual basis. So, natural question to ask is, so how do the dual basis and the basis compare, right? So we know, given, all right, that beta and beta bar have change of basis matrix Aij, we ask the question, what's the corresponding change of basis matrix for beta star and beta bar star? Right, the dual basis, how do those compare? What's that? Add a star to A. I like that. I like that. Man, I wish that was the answer. No, I don't.
I'm quite certain it's like myriads of steps in between.
Would be.
As far as what you classified it at the end.
Well, I don't know. I mean, matrix with a star on it means so many different things in so many different books. There surely must be some book somewhere where what we'll find is actually a star. It's probably true. Right, but I'm going to try to follow the calculation here. And we could call it anything except for 7. All right, so we're going to introduce some notation here. So let's let B. Sorry, I'm trying to be a good citizen of the up-down index world and write this correctly the first time. He has 2 sections in here. His first section has everything down, and then he puts things up and down in the next section. But I'm trying to give you the proofs from the start with up-down indices, so it's requiring me some flipping. And I almost bought a copy of this for each and every one of you, because I'm planning to follow it for the good part of for most of the rest of the course. This is manifolds and tensors and forms by Renteln. It is stupidly lucid. I mean, it's so clear compared to other books that I've seen. But anyway, so where was I? Let's let Bij be the necessary coefficients to relate the theta bar and less writing be such that. I mean, less talking, more writing. theta bar. What just happened here? Oh, he's used theta for the curses. As much as I'm following him, I'm not following it. Let's be such that E, let's see, E upper, where was I? E upper J bar is equal to a sum I equals 1. Sorry, it's taking me a second to translate this. E upper I, B lower I, upper J. I don't want to think about them in those terms at the moment. So, I mean, let's not get started into that. They're just coefficients that relate the dual basis and the other dual basis. That's all. Okay. That could be identified with matrices in a few different ways. I'll say that. Okay. But so if that's the case, then if we look at a dual vector, if alpha is an element of the dual, all right, then we can expand alpha either in the beta basis or the, beta star basis or the beta bar star basis, right? So we can, this then, alpha is equal to what? It's equal to, on the one hand, the sum I equals 1 to n of alpha lower I, E upper I, but it's also equal to a sum I equals 1 to n of alpha bar I, E bar I, right? So you can compare these different bases, right? Different components, all right, to the dual vector alpha. And when you do that, what's the relation? E bar, alpha bar, let's say lower j is equal to a sum of B inverse but you notice the B matrix has the opposite. A has has up down. The B has this down up pattern. So I think to be consistent, I should also write yes. And then what do we have here? Alpha I. Okay, so this and this are like 3 and 4, yeah. You want to call them, they're like 1 tilde and 2 tilde or something, yeah. Yeah. I'm mostly calling these 3 and 4, so if we want to talk about these later, we've got a label, okay? All right. So the question then is, how do the dual bases relate? I mean, how A and B are not, they are somehow related. How are they related? Well, the thing that unites everything is this Kronecker delta, right? So you can use that to find a bridge between these worlds. So that the delta ij, it's equal to, let's see here. I'll start with the, how about E bar, E bar I, E bar J, and what's that give us? E bar I is what? It's the sum over I of what? EI, BI, J. And then that acts on the sum of what? Let's say K. And this is expanded as what? By number 1, right? E sub K, yeah. J, right, the J. There's a conservation of indices going on here, I like to say. Indices are neither created nor destroyed, yet you can create and annihilate pairs of contravariant and covariant indices, which sort of correspond to no indices, is the concept. Yeah? What is it, Joe? I'm afraid to ask. No.
The index for E bar I, are we not going parallel to that? So it should over there be summation J, EJ, A to the super J lower K.
But the thing is, I already wrote a J here. This J has to match that index in 1.
But in 1,
Oh no, 1 is wrong. You guys should have stopped me on this a while ago. What is this? What is this? Oh man, I can't believe that. That's awful. That is J, yes. Yeah, otherwise that doesn't make sense. Thank you. No, I probably corrected that error in every step past there. I mean, it's already corrected here in the purple. Okay.
With the first part, the upper I and the J, is that the same J?
Oh man. Good grief. All right, so this also needs fixing, doesn't it?
Yeah, you just sum over something besides that.
Ay, ay, ay. What is wrong with me? My goodness. It's almost like I'm making all these mistakes on purpose to see if you guys understand.
You don't plan far enough.
Yeah, Joe's right. See here. That should be I, obviously. All right. That's not up for grabs. That is this I. That's not debatable. This we could make anything you like. I'm going to use an L. There we go. Now, this is a sum of linear maps. All right, so the way that works is I can just pull these scalars out. I mean, technically speaking, it's more like scalar multiples of functions added together. But the point is, these scalars can be pulled out, and so can those, and what do you get? Sum over L and K of B, L, I, A, upper K, lower J, and then E, L, E, K, E, lower K, like that, right? Now this is a Kronecker delta LK. And you can use that to collapse one of the sums, right? I have a double sum, but with that, one of the sums collapses to 0. Or it doesn't collapse to 0, it just collapses to one term. So we can rewrite this as, say, a sum over, I don't know, K. So I'm going to put, this basically just says L is equal to K. Otherwise, it's 0, right? So what do we got? We got B, K, lower K, upper I, yep. A, upper K, lower J. Right. Now, these are just numbers, so I can rewrite them any way I like. I'm going to rewrite them this way. This is the sum over K of A, K, J, B, K, I. we're about to scratch the itch that Jess wanted to scratch about 10 minutes ago. If we think of these as matrices, we've got row, column, right? This isn't quite the product of A and B yet, right? If I do think of A as the matrix A1, 1, A1n, ANN, A, N1, I suppose, row, nth row, column. Okay. This I need to transpose in order to get the usual product of matrices, right? So this is the sum over K of A transpose. Yeah, I suppose lower J, upper K, and then B, K, I. We're now seeing the reason that Renteln chose to derive these things outside of the up-down index notation. Because all of this you see how much trouble it is in the thinking to have up-down here in this derivation. If everything was down, I would have just breezed through this with a lot less thinking. So there's a cost to the up-down index notation, and we're currently paying it. But this is exactly A transpose B, the what? The what?
So,
Yeah. Now, of course, that's equal to Kronecker delta ij. I mean, but this is kind of, anyway, long story short, A transpose B is equal to the identity matrix. That's the relation between the A and the B.
Question, what does the up-down index get us if we have to pay a cost for it?
Yes, that is a good question. Now, well, you've already started to see it. You could anticipate where my formulas were wrong, right?
But that was more because I essentially just translated everything you put in up-down to lower.
Oh, really? Well, that's depressing.
I mean, it's just a pattern of which comes first.
Mm-hmm.
Top being the column and the lower being the row, I think.
Yeah, so, well, just B is called the contragradient matrix of A. I'm sorry. All right. So I've given you a horrible introduction to up-down index notation, but at this point I will now go and talk about the things Nathan would like me to have talked about an hour ago. Is that okay?
So we got to A transpose B is the identity. So and that's how we switch from the A over here to the B over there.
That's how the change of basis for the dual basis, if you take a basis beta and take another basis beta bar, right, and there's a change of basis matrix A from one to the other. This matrix B gives you the corresponding change of basis for the dual basis to beta star and beta bar star. And the change of basis matrices are related in this way. That's the result. The more important thing here, though, really, is just to notice that the basis and the components to a vector or a covector transform inversely. Okay. All right. See if there's still time for me to redeem myself and say something interesting. I mean, coordinate change is always a beast if you actually get into it, like we're doing today. Maybe I should just leave it for homework. I don't know. All right. So let me describe for you now then the idea of taking the tensor product. Like what are tensor products? So this is the so-called tensor product. Right. So a tensor product is something you can do with vectors and with dual vectors to make new objects. So, you know, if V and W and are elements of V, then V tensor W is an element of V tensor V. So V tensor V would be the set of all such things. Now the question, of course, is then, and also if we had, you know, but they don't have to be from the same space. I mean, I'm selling myself short here. If you had, you know, V sub j was an element of, let's say, Vj, where this is a vector space, and that's an element of the vector space, then you could also talk about, say, V1 tensor, V2 tensor, tensor, you know, V whatever. I don't know, 7. You know, that would be an element of V1 tensor V2 tensor tensor V7. It's kind of like it's kind of like a Cartesian product in some sense. I mean, you can string things together. It's not true that you know, V tensor W, for example, is not generally equal to W tensor V. It's not true at the level of elements. However, at the level of spaces, it is true that V tensor W is isomorphic to W tensor V. There's a natural isomorphism between these two things. What would it be? So if I had a thing in here, say X tensor Y, what would my isomorphism be between these two spaces? Yeah, that's it. So there you go, and you can prove that that's an isomorphism. All right, so I'm trying to explain to you at the moment formally what is a tensor product. I mean, it's something we can do to take two objects, put them together to make a new object. What are the rules of the tensor product? What are the algebraic things which make it what it is? Well, there's a couple of important things. So the basic axioms, if you will, of the tensor are what? First of all, if we have something like, let's say, C1V plus C2W tensor, you know, U, what do we get? But I should be more greedy than this. It's more than just this. I could have had, you know, something else over here, say alpha. Right. It could be just any particular thing, and we get what? C1 alpha tensor V tensor U plus C2 alpha tensor W tensor U. So it's distributive across additions of vectors. All right. It's not generally commutative. However, it is generally associative. So if I have alpha tensor beta tensor gamma, that's equal to alpha tensor beta tensor gamma. So without loss of generality, we just write alpha tensor beta tensor gamma. All right. Excuse me. So the let's see here. So we can pull scalars out, right? It distributes across addition of the vector space. And those are your basic things. Now, I wanted to mention this because, we can take tensor products of different spaces. Like it's meaningful, it's interesting, in fact, to look at, application that maybe you've already seen and you didn't realize it, is what I call V sub C, where V is a real vector space. This is a complexification of V, and to an isomorphism, this is really just C tensor V. And so, technically speaking, this would be something like span of, so if V has basis, let's say EI, right? This would technically be something like A plus IB tensor, let's say V has basis EI. Oh, maybe EJ is a better choice here. EJ, such that J is equal to 1. All right, so that would be what this thing looked like. It would be a span of, complex numbers tensored with the basis for V, whatever V is. You missed the bad part. Actually, this is a good time for you to have joined.
Well, we started the good stuff, yeah.
Yeah, there was an unfortunate event earlier. It's a necessary event. I will refer to it like we prove things that we didn't prove later, I'm sure. But anyway, so, that's not actually what we tend to write, right? The actual, if you, what I would tend to write is just what? Something like A plus IB tensor EJ is usually just written A plus IB EJ. So for example, if you take a vector space and you tensor it with the complex numbers, what you're really, one way to think of it is you're just changing the components to complex components. So that means that we're not writing the tensor symbol, right? That's just an application. All right, so just to focus a little bit more, let me focus here. If we're talking about V tensor V, tensor tensor V, tensor V dual, tensor V dual, tensor tensor V dual, and let's suppose I have R copies of this, and suppose I have S copies of that. A tensor in there is said to be type what? It's type RS. So T, an element of this, so T is type RS. Now, at this point, the constructivists among you are really, really annoyed because I have not explained what a tensor is. I've just been showing you a little bit about how you can calculate with them. Like they're associative, this tensor product is associative, it distributes. Like I said, you can pull scalars out. But what is it, right? Now, there's several different answers to that. Perhaps the most satisfying one is in terms of a quotient vector space construction, which you can find in Dummett and Foote. But the one I'm going to give for you here now is that there's a concrete model of these tensors of type RS as particular what are known as multilinear mappings. So what's a multilinear map? So, Oh, and there's. I guess I should be slightly more lazy here. I need to say a little bit more. This is equal to what? This is equal to so-called V tensor R tensor V dual tensor S. There's a shorthand for that. Now this I can also write. I can write this as something like T is equal to a sum. And here's where it gets interesting. So we got I1 dot IR and then sum I could have put it on the same sum. J1 da 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 JS. All right, and then T, we respect the index convention. All right, so T I1 IR. Whoa. Okay, J1 JS. Those would be the so-called components of the tensor. And then I do E I1 tensor, tensor E I R tensor. So then what we have E J1 tensor EJS. Now, I think you'll be very happy when I tell you that you can write this in multi-index notation as follows. As long as you understand what you're doing. But beware that I will use that multi-index notation in a slightly different and more technical way later. But you could use that kind of expression, right? So there's what it looks like. My point to you is that these things form a basis actually for the tensor space we're looking at here. And it's multiplicative in dimension. So like, for example, if I have a three-dimensional vector space and I take the tensor product of the vector space with itself, the resulting product space is nine-dimensional. All right. So what's a multilinear map? So if we have T, let's see here, T mapping from, let's see here, how's it go? Make sure I do this right. Otherwise I'll have to do a lot more writing. Yeah, so a mapping from V-dual, R-fold copies of V-dual, and then S-fold copies of V. All right, and then this is outputting a real number, is a R-valued type RS multilinear map if what?
Wait, is that intentionally switched from the previous age?
Yes. Oh, yes. That is intentional. So what you have to have is that T, oh, come on. T of what? T of, say, alpha. This is not, no, this is unfortunate. I need, I don't want this to be, I mean, all right, fine. It's clear from the context what I'm doing. 1, 2, how to say this? It's easier to say in words than notation. This mapping has to be linear in each entry. So if you hold all the other entries fixed, but you just let one have a sum, then you can break that sum up and pull the constant out. So like T of, let's say, alpha 1 C alpha j plus beta j, all right? And then you got all the way out to alpha r, and then you got your vectors, whatever they are. Let's say x1 xs. Well, that's equal to c t of alpha 1 alpha r x1 xs plus t of so much writing, alpha 1 beta j alpha r x1 xs. So what I'm saying is that I can pick the jth dual entry, and I can break up a sum, and I can pull out a constant. And likewise for the entries in V. I hope you'll forgive me if I don't write it down. All right. Now, does this form a vector space? Is a set of all such maps a vector space? Well, I would argue yes. In fact, it is. There's a larger vector space to think about, the vector space of all possible maps from this Cartesian product of the dual space and the vector space, right? So there's a vector space structure there that's just defined by the addition of functions. Pointwise addition of functions is a vector space, right? So these are functions of a very particular type. They have this multilinearity. And if you look at it, if you take two such multilinear maps and you add them, do you get linearity in each slot of the addition of those two? Indeed you do. If you take the scalar multiplication of such a t, do you get a tensor? Excuse me, a multilinear map. Sorry about that. A multilinear map of type RS again. Yes, you do. So these are closed under addition and scalar multiplication with respect to the pointwise addition of functions on this rather complicated space. So that's a subspace, right? So it is a vector space. In fact, the set of all multilinear maps itself forms a vector space. And so just to give it a notation, T is an element of, let's see, I think he calls it T, I don't know, what do you want to call it? What's his notation? T tilde RS, upper R, lower S. Right, and then he says that up here, T is an element of what? TRS. So the notation is using the index structure on the components to label the type. I have seen other books where they use the index structure on the basis to label the type. So beware. I mean, you can get confused about that. What's the isomorphism between these two things? This, I never really I described it formally, right? I never really told you what these objects were. I just told you how they behaved. This is a specific concrete object. It's multilinear mappings on this Cartesian product of vector spaces and its dual. What's the isomorphism between this formal object and this? It's very simple. So the isomorphism of TRS and T tilde RS is given by. So basically, I need to show what can I do. I can extend it. Basically, extend the following linearly. So if I've got ei1 tensor tensor e I r tensor what e j1 tensor tensor e j s, and I want to take that, right, and I want to describe something, an isomorphism of that does what? That acts on these things. So let's say this needs to, act on